So now we're going into infinite series. In this section, obviously, we passed sequences, infinite sequences. So we use this idea of addition, summation, that the terms, if they're added together, it becomes what we call as infinite series. Infinite, obviously, because we're going all the way to infinity and so forth. So instead of comma, 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 like the sequences, we have now addition. And so one of the best way to kind of understand what this means is by means of the ordinary final sum known as a partial sum. Partial sum obviously means partially. If I say S1, that means the first term. S2 means the first two terms, and so on. If I add them all together, I get some kind of a sequences of number that goes from 1 to n, where n eventually goes to infinity. So here's one example. Let's say you have 1 over, this really does not need to say that you start from n equal 1, because it should be obvious. So this is the same as saying 1 over 2 to the n, right? So if I write a bunch of terms, I get like 1/2 plus 1/4 plus 1 over 8, 2 cubed, 2 power 4, 1 over 16, and so on. So let me write partial sum. So S of 1 is A1, which is 1/2. S of 2 is A1 plus A2, which is 1/2, plus 1/4. What is that? 3/4. S3 is the first 3 1/2 plus 1/4 plus 1/8. Add them all together. What do I get? 7, 8, and so on. So S of n is actually 1/2 plus 1/4 plus 1/8 plus 1/16 plus all the way to what we call a 2 to the n, which was the series, right? So if I write this, these sequences of the partial sum is as follows. So first one was 1/2, S2 was 3/4, S3 was 7/8, and I think when I do based on the pattern, if I do S4, I should get like 15 divided by 16, and so forth. So if I do this and I try to find out what the n-term formula would be, if I look at the bottom of the fraction, I get 2, 4, 8, 16. So that's like 2 to the power n. Then I look at each number on top. Each number 1 happens to be 1 less than denominator, which is 2. 3 is 1 less than 4. 7 is 1 less than 8. 15 is 1 less than 16. So that would be same as saying 2 to the n minus 1. So that's how you find the nth partial sum. Based on that, I can kind of write this definition that if the sequence of the partial sum S of n converges to a number S, finite number S, then the series converges. And if the sequence of partial sum S of n diverges, it goes to infinity, then the series actually diverges. So in our example, let's see what happens if I take a limit of that. In our example, let me write the example. We had A was the series going from 1 to infinity over 1 over 2 to the n. But the partial sum S of n was 2 to the n minus 1 or 2 to the n, right? So if I take the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n to see what happens, whether or not it converges or diverges, I can maybe simplify this and write it as limit n goes to infinity of 2 to the n divided by 2 to the n minus 1 over 2 to the n. Just a basic algebra, I can divide them this way. And so the first one, obviously here, this and this would give me 1. So we end up getting limit as n goes to infinity of 1 minus 1 over 2 to the n. So now if I apply my limit n goes where n is, which is in the second term. So a, or whatever S of n was, is actually 1 minus 1 over 2 to the, when I apply my limit, LIM goes away. So 2 to the infinity, 2 to 2 is 4, 2 to 3 is 8, and so forth. Imagine if you get 2 and raise it to numbers extremely large. So the bottom of a fraction becomes a number that is extremely large in mathematics. That definition will bring us to 0. So S of n approaches 1. So we could say, therefore, A, we call it A, that series converges to 1. Okay, so that's how we kind of know. One of the important example of this inference is called this ratio test. Not the ratio test, sorry, geometric series. I'm getting ahead of myself in the ratio test, which is the important test we use for series. Geometric series talks about, you could recognize it by the form that they come in, which we talk about it in a few seconds, or also by writing a bunch of terms. If you look at the second term and say, well, how did second term relates to the first term? In other words, if you get the first term multiplied to a ratio r, you get the second term. And the same ratio, if it applies to the second term that produces a third term, and fourth, and a fifth, and so on, then that is the actual classic definition of a geometric series. And r, that ratio that you keep multiplying every term by to get the next term, could be positive and could also be negative. So one example that's a positive is something like we just did. So r being positive means like 1/2, 1/4, plus, I should say, plus 1/8, plus 1/16, and so on. So in this case, r obviously is 1/2. Why? If I take the first term 1/2, multiply 1/2, I get 1/4. I take 1/4, multiply 1/2, I get 1/8. 1/8 times 1/2, I get 1/16, and so on. So the a, which is always the first term, which we're going to need it later on, it's the first term, in this case being 1/2. So r being negative, well, if I take 1/2, let's say, multiply it to negative 1/2, I get negative 1/4. Negative 1/4 times negative 1/2, I get positive 1/8. Positive 1/8 times the same r, which is negative 1/2, it gives me negative 1/16, and so on. So from here, if r happens to be is 1/-1/2, and a again is the first term, also is 1/2, and so on. So these type of terms, if you write it, a multiplied by a ratio r, you get your second term. Second term times r gets you the third. Third times r gets you the fourth, and so on. So if you write a bunch of terms and you could recognize what r is, you could define it as geometric series. And they can they could have this kind of form that I wrote here. A and times constant, a could be 1, by the way, but if not, I would just write it a ratio raised to power n, and so forth. Sometimes you could reindex the numbers, and I'm talking about this because some of the examples, not that many on WebAssign, you actually might have the correct answer. You come up with n equal 1 to infinity, but the answer choices they give you, they all start from 0. So you say, how did that happen? So here's the example of how you can write a series and reindex. Reindex means if I play around with this first n. When I say 1, this means n has to start from 1. Let me make up one series, like 2 raised to power n minus 1. Well, if I don't want to start from 1, somebody says, can you rewrite the same series instead of 1, but you start from 0? N, first term, starts from 0. So what do we just do? We went the index number, we reduced it by 1. We subtracted 1 on the index number. Therefore, I have to go inside and add 1 every place I have n. So I go in, and it's 2n minus 1. I have to add 1. When I simplify that, I get 1 over negative 1 and 1 cancel, 2 to the n. So look over here, the first term here, when n is 0, a is 1 over 2 power 0, which is 1 over 1, which is 1. Over here, when n is 1, I get 1 over 2 power 1 minus 1, which is 1 over 2 power 0, which is 1. So a is also 1 here, a is also 1 here, so nothing changes. So here's, if I say, take this and write it when, I don't know, n starts from 5. When you say, wait a minute, n was 0, I added 5, I have to go inside and subtract 5. So this can be rewritten as n minus 5. And I guarantee you when n is 5, you'll see a would be the same thing as before as 1, right? So that's the idea behind reindexing. Don't panic, just look to see what the index number is and how they play with it. Geometric series is actually a nice series, and I'll show you the proof of this as to why that is. So all we do, look at this r to see the value of it. If the absolute value r happens to be less than 1, this is one of the only series that we actually know that it converges. And we all, not only that, but also we know that what it converges to. It converges to the sum, which is a over 1 minus r. Again, a is always the first term, and r is that ratio, right? And if it happens to be that r happens to be greater than equal 1, then therefore it diverges. And I'll show you the proof of it. So it would be very easy once. You don't need to obviously do the proof every single time, but knowing these less than or greater than equal allows you to automatically come up with the answer. So the proof. Let's say when r is 1. Well, remember S of n? It was a plus ar plus ar squared plus ar cubed, and so on. So we get S of n, you get a plus a plus a plus a plus a, da da da. So how many of them do you have? N of them. Then the limit of NA as n goes to infinity is infinity, which means diverges. So when r is equal to 1, so that kind of shows this portion of it that diverge. What about if r, absolute value r, is not equal to 1? Let's see what happens to this case. So we had S of n, again, is a plus ar plus ar squared plus ar cubed and plus a sub r to the n. So the proof of this says this. Multiply both sides by additional r. Okay, when I do that, I get r times S of n. I get a times r, I get ar times r, I get ar squared, and so on. Ar cubed, ar power 4, plus all the way a sub r times n times r. This, by the way, is a sub r n plus 1, if you combine it like that. So then we say, let's call this step 1. Step 2, subtract the 2. So when we subtract the two lines from each other, two equations from each other, we get the following. S of n minus r S of n. And the first term, this a, stays. And then I have a sub r. When I subtract the bottom one by negative r, this a sub r with this a sub r cancels out. Ar squared with ar squared cancels out. Ar cubed with this one cancel out. This one and this one cancel out. As you can see, everything cancels out. The first and the very last term stays. And the last terms get the negative because in the second one. So you get second equation. So you get a sub r to n plus 1. To try to get your attention, let me remind you that I believe a 10-year-old child came up with this proof. A 10-year-old child. His name was, I believe, Carl F. Gauss. Some books say that he was between 10 to 12 years old. Amazing. Something so simple. So look what he did next. He said, okay, I just multiplied this by r, and then I subtracted the 2, and then I said, wait a minute, there's a S of n, there's a S of n. Maybe I can factor S of n, and when I factor S of n, I get 1 minus r, and on the right hand side there's an a here, there's an a here. I can factor a. I get 1 minus r to the n plus 1, and then it says, what are we looking for to begin with? We started with S of n. So I divide both sides of the equation to this, and I end up getting S of n being a divided by 1 minus r times 1 minus r to n plus 1. So he got to this point, and then he came up with this idea of limit. He says, what happens to the limit as n goes to infinity of r raised to n plus 1? And he says this, that limit n goes to infinity of r n plus 1. And this is where analytically he talked about n. Remember we talked about here r not being to 1? So trichotomy. We talked about r equal to 1. So now we're saying, what if r happens to be less than 1? Well, if r happens to be less than 1, and you're talking about the limit, like 1/2 raised to infinity, that number r is less than 1, right? It's 1/2. 1/2 raised n goes eventually to infinity. A number that raises to power unbelievably large, it gets smaller and smaller and smaller and smaller and smaller. Therefore, from here, r raised to n plus 1 eventually goes to 0. So S of n becomes a over 1 minus r, 1 minus 0, or a over 1 minus r. So that's where that formula came from. He proved that way. And then let's look at the trichot. Last thing on that, with r equal 1, we did r equal less than. Now what about r is bigger than 1? Well, if that happens, r is 2 raised to infinity, it goes to infinity. Therefore, S of n diverges. So it was a very basic proof that he did, and that's where this a over 1 minus r came in for the when in fact the r, when it was less than equal 1. So not bad from a 10, 11-year-old kid that came up with this. So let's look at some of the basic example of this. Let's say we want to find some of the sum of this series. Let's say a equal, going from 0 to infinity, of 3/2 raised to the n. And you say, oh, I'm going to compare this to my a raised to r to power n. And if you don't believe that, by the way, you could write n equals 0, you get 1. N equal 1, you get 3/2. N equal 2, you get 9/4, and so on. You write bunch of terms, try to remember r. And if there is a r, then it says, oh, that's a geometric series. So if I compare these two, and I can see that from here, my r happens to be, our absolute value of r, which is 3/2, happens to be bigger than 1. So then you say, due to or by geometric series, a diverges, and I'm done. I don't need to do anything else after that. So that's the nice thing about recognizing r in geometry, if that is easy to see. Sometimes it's not. So let's look at another example, 2. Let's say we have, again, start from 0, 1, 3 divided by 2 to the n. So in this case, I can maybe rewrite this just to make it easier to see. 3 times 1 over 2 to the n, or that's the same as, by the way, 3 times, we've done this before this, from Math 126 or 96, we have recognized that we could write it as 1/2 raised to power n. And then you say, oh, I will compare this to my standard, geometric series, so that I can recognize what my r is. My r happens to be 1/2. Absolute value of r, which is 1/2, in this case, happens to be less than 1. Then, since r is, or absolute value, or less than 1, then a converges to S. And S was a formula that we need to know. 1 over 1 minus R, where A is always the first term. And R is always that ratio. Okay, so what is the first term? A is when n is 0. We go into the formula here. When n is 0, we get 3 divided by 2 power 0, which is 3 divided by 1, or 3. So S would be 3 divided by 1 minus R, and R was 1/2. So that's the same as saying 3 divided by 1/2, or 6. So we actually know, again, geometric series, when we recognize R is less than 1, we could actually say what it converges to. And in this case, we did. It converges to 6. So let's look at another example. Again, I'm trying to make them a little more abstract so we can get an idea of how what we need to do mathematically to manipulate the formula. Here's one. 2 raised to 2n times 3 raised to 1 minus n. Okay, so I haven't seen anything that looked like that, but then again, say, wait a minute, I can take this from pre-calculus and write it as 3 power 1 times 3 power negative n. Or say 3 times any number with a negative exponent is 1 over the same number with the positive exponent. And we've done this before. This is the same as saying 3 times 1 over 3, the whole thing power n, right? So, and then this 2 to the 2n, since we're dealing with n, can be written as 2, the whole thing power 2, the whole thing power n, or known as 4 power n. Okay, so this became 4 power n, and the next term became 3 times 1/3. So A can be rewritten as 4 power n times 3 times 1/3 power n. And these two, since both of them are power n, I can combine as 3 times 4 divided by 3, the whole thing power n. And from here, immediately you say, oh, since absolute value R, which is 4/3, which is bigger than 1, therefore A diverges. All that work to show that. Okay, so that's these are the. Let me do one more of these kind of manipulation. I think is important to kind of get used to these. Let's call this one B. Let's say you go from 1 to infinity. This is an infinite series of 3 power n divided by, let's see, I'll make it like a 4 raised to n minus 1. Based on what we talked about before, I can say that 3 to the n stays. This one I can write as 4 times n, power n times 4 power negative 1. Well, 4 power negative 1, again, anything with a negative exponent is 1 over the same thing with a power. Same power, positive power. Different, if it's a negative, it becomes positive and vice versa. So now B can be written as 3 to the n, 4 to the n, times 1 over 4. 1 over 4 kind of flips itself when it goes on top. So it becomes 4 times and 3 to the n divided by 4 to the n. Or we can call that 4 times 3/4 power n. And so based on geometric series, if I compare this to my A power R, n, my R happens to be this. So you could say since absolute value R, which happens to be absolute value of 3/4, which is 3/4, which is less than 1, therefore B converges to what? S, and that S was A over 1 minus R. And A, again, as before, is always the first term First term is when n is equal 1. You go back to here if you want. We use a different color. When n is 1, we get 4 times 3/4 power 1. 4 and 4 cancel out. You just get 3. Okay, so from here, s, which would be a, which is 3, divided by 1 minus r. Again, our r was 3/4. So we get 3 divided by 1/4, or s would be 12. So these are the example of geometric series and how we play with them to figure out if it converges or diverges. One of the nice thing about this, in case if we have a decimal point with terminal decimal repeat, or known as a repeating decimal, how do we express them as a ratio of two integers? In other words, here's an example. Let's say we want to express, let me write the language, express this number a, which is 0.08080808, keep repeating yourself. You have seen this thing with a dash above the